Hello, and welcome to this video in which I will show you how to solve simple KVL problems using CircuitsU. So here we have a simple circuit in which these two elements, the 5 ohms and the 10 ohms, are connected in series because each one of them share a terminal, and also the 2 volts terminals are connected by only one terminal on the other elements. So we have here what we call a circuit in series. All of the elements are in series. So the law of KVL, or Kirchhoff's voltage law, states that the sum of all voltages around a closed loop equals 0, right? So let's say that K is the number of elements. So if we go from K1 to capital K, all the sum of the voltages equals 0, or put it in, English, sum of all voltages in a closed loop equals 0. So here it is. Now, one of the things that many students tend to conceptualize is that the voltage or the source dictates how the current is, or which direction the current goes. So sometimes it is correct, sometimes it's not. The only thing that we need to remember is what we call the passive sign convention. So if we use this passive sign convention, no matter what, we stick to it, we will have all our solutions correct. So the passive sign convention states that, let's say we draw here a terminal, then a resistor, then here another terminal, and we assign the drop in voltage, because remember, voltage is always across the terminals. We assign this terminal to be positive, this terminal to be negative, and then we have the value of the resistance. And passive sign convention states that if the current enters through the positive terminal, then the power will be positive, meaning that the product of the power of the resistor will always result in a positive value. This means that if the power is positive by passive sign convention, then that device is consuming power. So it's being delivered power by something else. Now, the other thing, by again the passive sign convention, is if the current, let's say, enters the negative terminal, then we will have the opposite sign. So in this case, the product of the power, which is the voltage times the current, will be a negative sign. So this ensures that no matter what, the sign of the power will always match what terminals we assign to the resistors. Now, how does it work with voltage or current sources? So current sources and voltage sources are a little bit more complex than resistors, but as long as you keep to the passive sign convention, you will have no problem. So the way I use the convention is that, let's say we have a plus and minus voltage here, and here we have the two terminals. Then I know, because of the polarity of the voltage, that my negative sign here will be in this terminal and the positive will be on this terminal. For a passive sign convention, sources are deliverers of power. They use their power. They give their power away. So this means that the current must be entering the negative sign. So in this case, the direction of the current by the passive sign convention for sources is that it will enter through the negative terminal and it will go out through the positive terminal. Now, if we have a current source here, let's say a terminal here, then what we will have is that the current is already given, but then by the passive sign convention, sources are deliverers of power. They deliver power to something else. So in this case, their power or their sign must be negative. And so we can assign plus and minus terminals here so that it goes with the passive sign convention. Now, with this explanation in mind, then I will lead you to the last thing, which is KVL and KCL. To be honest, KVL and KCL just by themselves are not really useful, because they just tell you like descriptions of the world, right? Or how things behave, right? Like the sum of all voltages around a closed loop equals 0. Okay, that just means conservation of energy, right? But it's not applicable directly to any real or model physical circuit. KCL, same thing, right? Current enters in equals current enters out in a node. So that's pretty much conservation of matter, right? So regular physics. So just by themselves are not that useful. What they are useful is, or when they are useful, is when we assign a relationship between them. And the relationship in devices and in materials in general is this little formula, which is Ohm's law. this Ohm's law applies to resistors, linear resistors, which model any device or any element that consumes power. And so now KCL and KVL mixed or joined together by Ohm's law, now we can have something more tangible that will let us make some analysis. So it's not just KVL or KCL by themselves. We use them along with Ohm's law in order for us to obtain physical results or meaningful results. So with that explanation, let's go to the circuit. So what we're going to do here is KVL, because it's a closed loop. So I will guide you step by step on how to solve this circuit. So right off the bat, we have a voltage source. We don't care. So this is I/O, right? And of course, the current will always have a sense of direction, either going clockwise, counterclockwise, etc. We're not going to worry about the direction of the output current or the result of the current for now. We just only want to derive the equation that describes this circuit. So we know for sure by passive sign convention that the current in a voltage source will go from minus to plus. So this gives us a sense of direction of the current in this circuit. So this means that the current will go clockwise. So now that we know that the current flows clockwise by the passive sign convention, we can assign plus and minus charges to the resistor such that when the current enters, because this is clockwise, goes like this, it enters the positive terminal. This one here enters the positive terminal, and then this current here on the source will enter the negative because it's providing energy. This may not always be 100% all of the cases. As long as you stick to the convention, you will have the results no matter what. So in this case, we have our three elements, and we're going to assign them voltage. For example, here, this is a voltage across the 5 ohms. We don't know what it is for now. This is a voltage across the 10 ohms, and here the value is already 2 volts. So with KVL, the sum of all voltages along a closed loop equals 0. So here we are writing the voltage expression for the resistors, and remember, for sources is going to be negative because it enters the negative terminal, equals 0. Now, this is KVL, but what's the voltage across 5 ohms? What's the voltage across 10 ohms? We don't really know for now. So we will use Ohm's law, in which V equals IR. So in this case, we will have that the current is going to be the same. Oh, this is another thing. Current is the same across all elements in a series circuit. So in this case, the same current that flows through the 5 ohms is going to be the same current that flows through the 10 ohms, which is going to be the same current that flows through the 2 volt source. So we can just use one single term for the current, which is I, and then we're going to multiply by the resistance. So this is going to be 5 ohms, and then plus I, which is going to be 10 ohms. So we are just replacing V by IR, minus 2 equals 0. Now in this case, we can simplify things a little bit. So we will have here, I like to put my the numbers first. So 5I plus 10I minus 2 equals 0. Now we can solve for I. In this case, we can group the 5 and the 10 to be 15I. And then we can move this minus 2 to the other side by adding 2 on both sides. So 15I equals 2. And since the current is the same across all elements, this current is also going to be I naught. So now we can replace I with I naught. 15 I naught equals 2. And then by dividing both sides by 15, then we can solve for I naught. So I naught equals 2 over 15, which in this case, it will give us 0.1333 repeating amps. So now we have to know what is the direction of I naught, because it also is important. So in this case, the current I naught flows to the right. So it flows clockwise, which is the same convention that we did for the passive sign. So in this case, I naught goes in the same direction as we did in our passive sign convention. So we don't need to change the sign of the final answer. So in this case, we will put here the current to be 0.1333, and then we will submit. And then in this case, we have gotten the correct answer. And as you can see here in the visualization, the same current flows through all elements. So hopefully with this video, I've helped you understand a little bit more about KVL with Ohm's law, how KVL by itself teaches you a little bit, but in order for us to really apply it to a circuit, we need to combine it with Ohm's law and the passive sign convention. So those three concepts are very, very important in the underlying basic understanding of on how circuits work. So if you have any questions or comments, please let me know. Thank you very much for watching the video and keep practicing.